Okay, let's get started. So, I think we have the same people here this week as we had last week, which is good. So I don't have to go over any of the orientation stuff anymore. And we're done with that. Excellent. We are done with that. So, chapter number 2, which is what we're going to cover today. And I'm going to actually go into chapter number 3. Chapter 2 is really small. In fact, it has nothing to do with data structures. It talks about the analysis of algorithms. But probably important. The author felt it was important. I also feel it's important to kind of talk about at least the concept of how to evaluate algorithms in terms of, especially when we're talking about data structures, because algorithms and data structures have a tendency to work together, and for the most part, it's one of those programming language constructs that are used frequently. So it's also important to read chapter number 2 in the book. You guys bought the book yet? No? Well, I have one copy of it I can loan out if you want, actually. Check it out after class. I can loan it out, but I can't loan it out for the entire term. I'm going to need it back eventually. So, all right. So maybe I should loan it out next week. Actually, I need it this week for something. So I still haven't finished all the assignments yet. So let's see. This particular chapter, number 2, talks about the software development in terms of respect for efficiency. The only reason why we care about data structures or about algorithms in general is we want to make the code less spaghetti-like, as I mentioned last time, and we also want to make it run efficiently, which in terms of software engineering and programming, efficient equates to speed normally. We want something to run fast. And we also want to take up small hard drive space, and we want it to not consume resources on the PC, a bunch of other criteria. But efficiency is normally the speed in which the program is running or it's doing its computation. So we're going to look at the concept of the algorithm analysis and the concept of the asymptotic, I can't pronounce that word, complexity. Let's just call that the complexity of algorithms, generally accepted U.S. terms. And then compare the growth factors and the functions that might exist in between them. So, again, it's just one small chapter, unrelated to data structures, but it's part of the orientation for this particular course in terms of the concept. And then we'll move on to collections, our first structure after this. So the aspect of software quality is the efficient use of the resources, including the CPU, which means the calculations that are being performed. We want to make sure that not only are they performed correctly, but they are done in an efficient manner. And so an algorithm itself and the analysis is the core to the computing topic. It's very closely tied to data structures, so it gives us a basis for comparing efficiency of algorithms. And so we have things like big O notation, we have complexity and things of that nature to kind of consider in terms of figuring out which algorithm selection might be good. And here's an example, which sorting algorithm is more efficient. I gave that answer away actually last week. I said the binary search is basically the more efficient version of it. Let's talk about growth functions for a second. So analysis is defined in terms that are based upon, let's say, the problem size, the number of items to be sorted. So if we have a huge list of items, you would think naturally it's going to take longer to sort that list. And it should. If you're using an ordered sort, if you're using a one-by-one sort or search through that list, for which we're trying to figure out, which item is bigger than another item, or which item matches one item we're trying to find. Which means we have to visit every item, which means, in theory, that's going to be, if the list is long, it's going to take longer to do that, which is kind of the nature of algorithms in general. It depends on how big the data set is. How much data are we transferring? What are we doing with it? Another key operation might also be to compare the operation. Are we searching it? Are we sorting it? Are we reversing it? What kind of operation are we performing on the list? Also leads to its efficiency. And so we have this little formula on the bottom of the screen here called the growth function. Allows us, shows us the relationship between the size of the problem and the time it takes to solve the problem. So in theory, and this is a theory again, we can take the time it takes and we can do this calculation here, simple little math program, function I should say, and kind of figure out, given this number of items, given what we're going to do, compare. In an example, let's say comparison of two values in an item, searching for something, And given the size of the list, this is how long it's going to take in terms of the efficiency. And then we can measure the efficiency with different techniques that we might be doing to come up with some sort of an analysis of the algorithm and the technique. And you can see the comparison in terms of the growth function as the search space increases. Here we have the number of dishes. As it goes up, the main calculation goes up and becomes of significant importance. So algorithms, especially the efficiency of algorithms, is something that's kind of core to computer science, if you think about it. In most undergraduate computer science courses, they offer analysis of algorithms, kind of sort of a course where you compare the runtime of different algorithms, the efficiency, and then you kind of figure out which methods are better for certain applications than other methods, and how that's going to work in terms of the efficiency. Because what we're trying to do is just make it run faster in terms of the efficiency. So to continue on with the concept of the growth functions, it's not unusually necessary to know the exact growth function. It's an estimate, or actually I would say it's an approximation. So the key issue is the complexity in terms of the, I'm going to try and pronounce this word, asymptotic complexity. I just say complexity because I can't pronounce that word. So it's complexity of the function and how it grows. Can someone please shut that door back there? Hey, TA, could you shut the door? It's kind of loud out there for some reason. It's irritating me already. Okay, so how it grows as the number increases, how the complexity and how the particular growth trends transform. So determining the dominant term in the growth function is the factor that we're interested in looking at. If we can control that, then we can essentially control how efficient or how lack of efficient the algorithm might actually be. So this is often referred to as the order of the algorithm. So the order, and then we also use the big O notation, as I mentioned already, to specify the order. So we have this generic calculation for big O notation. It says we can put it in big O notation, we can specify the order of the degree of complexity that might exist in terms of the efficiency. Basically, it tells us one solution might be better than another. If we can calculate a big O notation for it, we can go, well, this is O1, or this is O log n. We could kind of figure out how complex it is, and then basically what kind of speed or what kind of efficiency can we expect. So here are some typical functions and their complexity as related to the growth function. So for the purposes of this class, you don't actually have to calculate big O notation. You don't have to calculate anything in terms of efficiency. I'm showing this to you as a kind of a roundabout background information in terms of how you would go about assessing the efficiency of algorithms, just in case you haven't had this as an undergraduate computer science student. Some of you come from different majors. You may not have been exposed to algorithms in general as a concept, but it does relate to data structures only because we're thinking about certain same concepts in terms of the efficiency, although we don't measure them the same way. So increase here, we have an increase in the problem size with a tenfold increase in processor speed. So you can see things can get out of control quite quickly once the problem space gets bigger. That's issues that happen in here. Here's a really good example here. Comparison of the typical growth function for small values and how it kind of can change in terms of comparison as the values get bigger. Which basically means the larger, the more complex the issue in terms of the sorting and the subsorting that might be going on, the more time it's going to take. So it's a way of assessing and figuring out which one we're going to use over another in terms of comparison. So here's another one with the large values. You can see they're almost, here we have more of an arc with the larger growth, with the larger values. It's kind of like increases exponentially. I mean, the time it takes to do it just goes out through the roof in terms of the input size. So analyzing the loop execution, here's a kind of an example to put this into perspective in terms of what we want to do. So the loop executes a certain number of times, let's say executes n times. In terms of, we're going to count the number of loops. Thus, the complexity of the loop in terms of n times is the complexity of the body of the loop. So when the loops are nested, the body of the outer loop includes the complexity of the inner loop. So if we take the example a little bit further, we can say this is ON in terms of the loop 1. So we have one loop. So the following loop is ON. O notation. This is big O notation, by the way, because the loop executes n times and the body of the loop executes once. So we have for typical C++ looking for loop. We can say that's O to the n. And then we can also say if we nest a loop inside, we have n squared coming out of that because we have twice. We have the inside loop and we have the outside loop. So as an example, you can kind of see how the complexity, doubled essentially in terms of the execution time. So the following loop has O to n to the second because the loop executes n times in the body of the loop and it includes the nested loop. And this is just an example of how computer science people go about essentially measuring, judging efficiency in terms of the algorithm. Why do we care about this? This makes our program run slower or faster. And the technique that we're using affects the overall usability, function, feel in terms of the sorting and searching. And what we're doing with these data structures, let's say for example we create a list. Well, we're going to have to sort the list. We're going to have to search the list. So people who write really good data structures, they also think about the algorithms. You have to actually think about the complexity of the algorithms and what technique are you actually going to do to reduce the amount of time it takes to actually use this particular data structure and get the functionality correct. Because it's not about just storing the data, it's about getting the data, retrieving the data out of the structure. So, which kind of tells you the two sort of do work hand in hand. Which means, if you take a data structures course, you probably should take an algorithm design course too. If you haven't, an algorithm analysis course, because one without the other is kind of like half there, I think. So to analyze a method call as an example, let's say we're not doing a loop, we're just doing classes with methods. Simply replace the method call with the order of the body of the method. So the call, this particular call will be 0, big O to 1 level because we only have one method call. So if we had multiple method calls or nested method calls, we would increase the complexity of that as well. And I know that was pretty short. It's a pretty short chapter as well. And it's just here's the concept of algorithms. Here's why we're analyzing them. This is what we're looking at in terms of, and obviously that's not a good replacement for an algorithm course, but kind of gives you sort of the impression that there's a relationship between the two. And that, it's not a bad idea to kind of focus in terms on efficiency design as well. So what I really want to cover today is Chapter 3. Moving right along. Chapter 3 comes up with the first concept of the first data structure that we're going to look at, which is also, I believe, the theme of the first assignment that you're going to need to do. And it has to do with collections. And the reason why I picked Java as the programming language is because Java supports built-in data structures like collections. And a collection itself is just the starting point. We can build on the concept. And collections actually have an inheritance to them, which is easy to see in the Java programming language. And as noted before in day number 1, you don't have to use Java. You don't like Java, like some other language, use whatever language you want. All the assignments can be done in any programming language you want, but I'm going to focus on Java only because, well, some of you guys already took the Java programming course. If you're not, you're taking it now. And it's a little easier to kind of relate it to in terms of something that you're going to understand, hopefully. So what's the objective of this particular chapter? Well, it's to define the concept of what it is we're talking about in terms of collection, what a collection is, why we want to use it, what's it designed for. Explore the basic structure of the Java Collections API, which is great because we have an entire API that we can create instances of collections and things and not have to worry about manually reinventing the wheel. If you're using C++, Basic, Visual Basic, some of the other languages out there, you have to actually create your abstract data type called collection. You have to create everything. It's not too hard. You can do it with classes, you can do it with structures, all sorts of different things. But in theory, it's a lot more work than creating an instance of an object called collection. So we're also going to discuss the abstract design of the collections and define a set of collections and then use a set to solve a problem and examine an array of implementation of a set. So we'll take the collections into the concept of the array implementation and the concept of a set and how it relates to the concept of a collection. And this is essentially the core, easiest data structure in this particular course. And not to say that it's hard, it doesn't really get much more complex than this, but it does get a little bit more because we start specializing the structure. mean, a collection is pretty broad if you think about it. I mean, it's like taking a bag and throwing a bunch of stuff in it. That's a collection. I mean, it's just, usually it's not sorted. Usually it's just a bunch of items that are all thrown in together. And we call it a collection. So here's our formal definition of a collection. Let's see what the textbook has to say. It's a collection is an object that gathers and organizes other objects, elements. So a collection of books, a collection of chairs, a collection of students. So sometimes we just create a generic collection to house something, like a folder, in terms of an application that you're developing. Many types of fundamental collections exist. So they are also defined as, and here's the ones you are familiar with, probably: stacks, queues, lists, trees, graphs. They're all, by theory, collections, which is why we start at the lower level. I mean, you can kind of think of this sort of like inheritance, if you want. It's a collection that turned into a queue, that turned into a stack. Or you don't usually have a queue that turns into a stack, but you'd have a collection that turns into a stack, a collection that turns into a queue, a collection that turns into... And what are these things? Well, a collection itself is just a grab bag. It's just a open the bag and throw a bunch of stuff in it. That's a collection. If we start sorting it, so we start using an algorithm to, let's say, sort it or something, then we end up with a list. So, you know, the difference between a collection and a list is some sort of an order that's done to it, some sort of an organization that's applied. And then the list turns into a queue or it turns into a stack, depending upon how we order it. And how we're ordering it is going to determine how we're going to put items into it and take items out of it. So the difference between a queue and a stack is real basic, actually. In fact, most of you know this already. It's just the order in which we're putting something in and taking something out. So we can broadly categorize as a linear. Linear means a line. Organizes the elements in a straight line. Or it could be nonlinear. Collections don't have to be linear by default. They can be sets. Sets aren't normally linear. Linear is more of a list, or a line. You know, if you took all, it's like how people organize checkers and chess. You know, when you put the game away, do you throw them all in a pile, or do you take and line them all up, or do you take the chess pieces and you sort all the pawns over here and all these guys over here, and the reds over and the blacks over here, all the different, you know, pieces. That's essentially what you're doing with a collection. So here's a linear and a non-linear collection, excuse me. So a linear and a here's a linear, and here's a non-linear kind of look. So this is a one leads to another, leads to another, leads to another, leads to another. It's all lined up. Here, it's kind of hierarchical. It may not be. It could be a non-linear approach to this, and this looks like, you know, a common data structure called a tree. That looks like a list. So these are both collections, however. They both qualify as collections, but one's linear, one's not linear. So, and the purpose of this lecture, part of it is to give you the vocabulary as well. So when someone says something is non-linear, you go, a tree? Maybe, hopefully. First thing I can think of it would be some sort of a tree structure, which it's not lined up. It's not lined up. It's non-linear. So. Elements within a collection are usually organized based on, and here's some criteria to organize them. Because you're going to throw all the checkers in the, let's take all the checkers and the chess pieces and throw them all in the same bag and call it a collection. That's a valid data structure. Let's organize it. I mean, I'm probably going to separate out the chess pieces from the checkers pieces. So, because we can tell the difference. And we're going to sort it by maybe the type, and then maybe the order, perhaps, some sort of thing. So the order in which they are added to a collection, or some inherent relationship among the elements themselves. So an inherent relationship among checkered pieces is that they're all checkered pieces, checkerboard pieces. I'm going to say, you guys are familiar with checkers? Chess, the games? These are board games. Okay, good. I was in a class one time when someone did have no idea what what checkers was. It's a game. People heard of chess because it's in movies all the time, but some people have never heard of checkers. And in the old days, that's what we played: checkers and chess. Right now they play Monopoly and other games, Go and Don't Go, and I don't know. So here's an example. Couple more examples down here. For example, a list of people may be kept in alphabetical order by the name or the order in which they were added to the list. Well, people we organize them alphabetically by your last name normally. That's how people get ordered. Which type of collection you use depends on what you're trying to accomplish. If you're trying to organize people and cut the group in half, most people think it's fair to go by the alphabetical order. I don't really know if that really is fair. I mean, especially if your name starts with A, you're always in the first group, or Z, you're in the last group or something. So it's kind of predictable, actually. But it really depends on the application that you're looking at in terms of how you're going to sort the group and how you're going to do that. And you find this is like, school teachers, they do that. They like to count like every other head. I think that's more fair, actually. 1, 2, 1, 2, 1, 2, just friend. That's a valid way of sorting a collection, actually. So, abstraction. And in fact, I'm going to get into the concept of object orientation as well, because data structures these days, especially if you're talking about objects, in Java, it's all object oriented. So I'm going to hit that a little bit as well. Concept of abstraction is interesting. I started this lecture out by talking about abstract data types. Data structures are abstract data types. It's the abstraction that you're creating of a queue, of a list, of a pile, of a set, of a collection, of a class. If you, not a class, but let's say you called it a group, a class, classroom, if you want to call it that, instead of using the word class. It's just the abstraction that you're applying to the way that you're sorting the collection. So it hides certain details of certain times. So if I say a queue, abstractly you all know what a queue is. If I say a car engine, you know what a car engine is. You don't have to know what is inside of a car engine to know what a car engine is. Which the opposite of abstraction is detail. So if I said you have a radiator, a carburetor, a fuel line, and oil, and I start mentioning a bunch of... most people go back and say, are you talking about a car engine? Raise it up. So it's usually the level. When I say raise it up, it's like you come up higher. Higher you go, the more abstract you are. The lower you go, the less abstract you are. So the concept that's used to describe data structures is the concept of abstraction. So the collection itself, like any well-defined object, is an abstraction, and it provides a way to deal with complexity of a large system, but deal with it kind of on a smaller level of detail. It's the queue, it's the stack. So we want to separate the interface of the collection, which is basically how we interface with it, from the underlying details of how we choose to implement it. So if we're talking about a queue, this is the interesting thing, and I don't even know why they do that, but there's a special language that you come up with. Stacks are always like a pop and a push. Queue is an in queue and a in queue and an end queue. It's like I've never liked in queue and end queue, or pop and push. Who pops and pushes? But stacks, they would say, well, let's put something on and take something off. It's a pop and a push. And the more you read books and the more you kind of work with the structure, everyone calls it pop. Pop item, push item, pop item, push item. And it's like, all right. You hear that lingo going on, you go, oh, that's a stack. NQ, DQ, NQ, DQ. And put it in the queue, take it out of the queue. Okay. I don't know why they didn't come out with some universal language to say input it, export it, input it, export it. But I guess it's all putting a number on something or putting a label on something. Let's talk about the concept of the interface. So the interface is our NQ, our DQ, our pop, our push. It's those words that we're coming up with to describe the actions that we're performing, of putting an item into the queue, taking an item out of the queue. So we have well-defined interfaces that mask the implementation of the collection. This is where the Java programming language makes this easier, provides the interface for us. So we just say, create an object of this type, collection, and here's our interface. And our interface has these methods that we can call to pop, push, NQ, DQ, all these other things. So here's our our class that uses the collection, and then here's our class that implements the collection. And we have this interface that goes in between them. And this is right out of the book, so if you want more information, this lecture was going to cover it from a summary, but if you want the implementation details of the interface, get the book. That's what I'm recommending. So, Well-defined interface mass implementation of the collection. It provides a higher level of abstraction to the collection. So we don't actually have to know exactly how the collection is implemented. As an example, let's say we weren't working with Java at all, and we were working with C++. And I said, create a collection. Most people just sit there and go, okay. Well, we can do it with pointers. We can create some memory. And we can create, come up with a collection concept with pointers. Well, we could do it with an array, I guess. If you do it with an array, you're kind of limited on items. Well, we could create our own abstract data type, call it a collection, and implement it with something. And what you're looking at is how to design the interface. I mean, you're looking at, well, something's got to store it, and then after they store it, what about the interface do? We've got to get something into the list, into the collection. We've got to get something out of the collection. What if we want to print the collection? And then all those questions that you're asking yourself in terms of the implementation is the interface. So what makes Java simple is just learn the interface. Forget about the implementation. Just create an object, call it a collection. So, and if you think about the concept in other languages, why did the programmer ever have to create data structures? That's the part I couldn't understand. As a C++ programmer, I was like, why do I have to create my own stack? Actually, at the beginning, they didn't even have strings. You had to create your own string. It's like, otherwise you had a character array option. It's like, why in the world did C++ people have to? And still today, well, no, there's a string class today, but unless you have access to C++ and you're just working with like GCC C, you may not actually have the string class available to you. It's just standard C. So you'd think it would be built into the language, but languages have grown to the point now where more modern languages like Java have everything built into it. So it takes away some of the complexity, makes it more abstract. So here's some issues with collections in terms of the structure. After each collection we examine, we want to consider, how does a collection operate conceptually? When we put an item into the collection, and don't think about stacks and queues or lists right now. Think about a nonlinear collection. How are you going to put something in? Are you going to relate it to objects that are already in there? Or are you just going to add it? And again, when you think about the concept, when you have to design this yourself, usually most people would go with a numbering system. Here's the first item, here's the second item, here's the third item, here's the fourth item. But what if you don't want to use a numbering system? Then you're creating a list from a numbering system. So the design of the collection is kind of interesting if you think about it by concept. Because someone had to make this stuff up conceptually. Because there is no right or wrong way of doing it. You can add to the front, to the back. There may not be a list at all. You just label it. Here, you're part of this. You're part of this group. You're part of that group. How do you formally define its interface? How do you label the pop, the push, the insert, the X, DQ, NQ, stuff like that? What kinds of problems does it help us solve? Why do you want to use a collection? You can use a collection in terms of going back to algorithm efficiency. If you don't need to know, all you need to know is the number, how many are here, then does it really matter the order? So you don't have to keep track of that, which means you don't have to store, you don't have to search through it that way. But the design of the collection, if you had to search it, is going to affect the efficiency of those algorithms depending upon how the collection is implemented. So if it was a tree, as an example, a nonlinear tree collection, then your search technique is going to be different. Trees are faster than lists anyway for searching, so yeah, kind of adds a little bit of mystery and I don't know, some complexity to the design. Another one is what kind of problems you're going to solve. Okay, so what ways might you implement it? Obviously, what are the benefits and the cost of each one of the implementation methods? When you look at the implementation methods, that's when the crossover between algorithms and data structures becomes apparent. It's when you start thinking about the implementation details. Because if it takes too much time to actually put something into the list, because the algorithm for inserting into the list is time-consuming, the structure is not very functional overall. So here's some terms. So the terms used in the study of collection are defined by a variety of different ways. And I kind of talked about a little bit of these already. So here's some definitions to complete your vocabulary. The data type, a group of values, and the operations defined on those values. We have data types that we're storing in the collection normally. The abstract data type would be the collection. So the data type whose values and operations are not inherently defined in the programming language, which means if we're creating an abstract data type, it's a type we've created from built-in types normally. And then the data structure, which is what you're studying in this course, the programming language construct used to implement a collection. The construct might be a stack, it might be a structure, it might be a class. It's got to be something, or an array, it's got to be something built into the language that you're going to be able to use in terms of the abstract data type. And that's the missing piece a lot of beginner programmers don't get. It's like the stuff doesn't come from outer space. You have to use the tools. So then they end up going, oh, I have to learn the tools if I want to use the tools associated with creating these abstract data types. And for some strange reason, a lot of programmers, new programmers, are afraid of abstract data types for some strange reason. It's like something they don't run out and say, I want to create one. So here's where it gets easy. You don't have to create one in Java. So we have the Java Collections API. Here in the Java class, you've kind of seen a little bit this already, but I'm going to refresh your memory on it. The Collections API is a set of classes that represent some specific collection types, and it's used in inheritance, and there's an entire hierarchy. It's implemented in various different ways. We have different types of collections that we can create, and different types of inherited classes from this. It's part of a large class library that we use with any Java program. We just import the package, and then voila, we have access to all of these different collections. API stands for Application Programming Interface, which is what API stands for, if you're brand new to this. And we can look at different types of collections. We're going to examine the appropriate classes in Java, and we're going to use Java essentially as an example. The stack collection. So now you know what a collection is, hopefully. And if I were to ask you on an exam, which one of these are collections? All of them are collections. Everything that stores things like stacks and queues and lists and trees. A tree is a collection. So let's talk about the stack first. So look at an example of a collection that is a stack. So a stack is normally by default referred to as a last in, first out. It doesn't have to be, as we've seen so far. So the collection of elements is last in. First out manner, or LIFO, last in, which is what LIFO stands for. It's very similar to a stack of plates, a stack of books, a stack of anything. And it's a linear list, and it may only place new elements at the top of the stack, which is why we push something on, and then we pop something off. We can only remove elements from the top of the stack, which is going to be a remove or a pop. So here it is, a conceptual view of the stack, removing an item and adding an item to the top. Everything gets to one end. If you start playing around with the concept, you've ruined the integrity of what a stack actually is. Because you can implement it differently. You can implement the stack where you put it on here and take it off here, and then you're going to get a queue. So the concept of the stack as a data structure has a special purpose. And then the rest is one of the things that this course kind of brings to light when you use a stack. You're going to use a stack when you need to use the concept of a placeholder or a list of items that you're going to go through sequentially, and you're going to go through them in reverse order that you started with. So as an example, in programming in operating systems, you're programming an operating system for a runtime environment. You're going to create a stack. They actually call it a stack in the runtime environment. It's going to take your executable machine code as an example. It's going to push it all in an order, and then it's going to pop it off in that order. And then it's going to push on more stuff, and it's going to pop off more stuff. And you're running it sort of in batches if you think about it. You're creating stack entries to run commands. Let's say, example, you wrote a hello world program to, that's not hello world, you wrote a program to add two numbers together. So the first line says, and it got converted to assembly language, now it's in machine code, and your operating system is going to run it. You're going to use a stack structure for that, because you're going to take A, put it on the stack, okay. plus, okay, plus B. You're going to accumulate. So it's used to accumulate data items and then process the data items in the reverse order. So reads it one way, processes it another in the reverse order, pops it off, and then you're done. You know that that group or that section is complete. So things come on the stack, things leave the stack. It's a short-term type usage. You don't create a stack for something that's going to hold data indefinitely. No reason for it. I mean, you push it on, you pop it off. It's a kind of a lightweight structure that's kind of used to process information in batches. And you make the stack as big as the batch. So the stack fills up, unload the stack. Fill it up again, unload it. Fill it up again, unload it. So it's different than a queue. In a queue, well, I'll talk about that next, but a queue's got different meaning to it in terms of how it's supposed to be used. In terms of the collection operations, let's think about the stack for a second. Every collection has a set of operations that define how it's going to interact with you. Stack's got the push and the pop. So you push a bunch of stuff on there, pop it off. Push it on. So think about it like a temporary holding bin. Usually includes ways for the user to add and remove elements, which is what we have. Determine if the contents of the collection is empty. That's good. Determine the collection size. Do we really even know? Do we have to even know the size of a stack? No. What do you need to know the size of the stack for? When we're done with the stack, we're done with the stack. It's like the job is based on processing the stack entries. When the stack entry is done, we move on and we load the stack back up again. In a queue is different. In a queue, we kind of figure we want to know the size of the queue. Because we want to know, and I'll just talk about queues for a second in contrast to a stack. In a queue, we're interested in the order. It's a first in, first out. So the first person who gets in line is the first person who is served at the counter. And we watch queues. We want to know the size of the queue. Because we might have to open up more windows. Or we might have to, and what we're primarily interested in is nothing more than a linear list of order. And it's done kind of one after the other in a sequence, sort of like a stack is, but for a different purpose. We fill up a queue, and we may not necessarily ever empty it out. Queues age, stacks don't age. Stacks, we fill it up, we take it off. Fill it up, take it off. Queues, we fill up, and we just fill them up, and we fill them up, and we fill them up. It's kind of like the line that just keeps growing and growing and growing. So when you create the queue data structure, you're going to create it so it grows unlimited. Any number of people could be standing in line at one point. It's going to grow. Stack doesn't have to grow. Stack can be limited to 5 entries, 6 entries, because it's a special purpose for processing batches. We know how big the batches are. We create the stack, we put the items on the stack, we remove the items from the stack. Queue is meant as a holding zone. It's meant to fill up and hold it, kind of like a swimming pool holds water. Put it in there, let it sit there forever, and then we can manage the queue by figuring out how many people are in the queue. What's the average turnaround time of the queue? What's going on with the queue? Maybe we can make this queue run a little faster, and then we can build in operations on the queue to monitor it, to control it, to operate it. So there's usually a little bit more stuff that goes into the implementation of a queue than a stack. So if you wanted to order this in a hierarchy, stack would be underneath the queue in terms of complexity. It's easier, and it's faster, because we don't have the overhead of keeping in track of the order. We don't care about the order of that stack. It's just push it on, take it off. And we don't care. We don't have to keep track of the order of the items. We don't have to keep track of how many items are in there. We know the size of the items already. It's pretty predictable. Here's our stack operations. Push, pop, peek is empty in size. So if we were going to create this in C++, these are the methods that we would do from the class or something that we would create. Push is going to add an item onto the top of the stack. Pop's going to remove it from the top of the stack. Peek is going to examine the element at the top of the stack. We don't have to peek. And this is the interesting thing is you see these people that create this, all-in-one data structure. Wrong approach, actually. If you're going to use a stack, you're not going to want to have a search technique that goes through the stack looking for something. Now, is this person in the queue? That's more of a queue. Searching a queue is more of a, it's a different kind of concept. The stack is more like we're only interested in the last item that's on it. What's the last item? So we peek at the last item to see what it is. And we peek to see if there's a last item. If there's no last item, we know it's empty. If it's empty, we can start the routine all over again. And we can do something else with it. And then decide to determine the number of the elements on the stack. How close are we from finishing this particular operation? And you'll see actually in most 99.9% of all implementations out there, those are the terminologies that you're going to see for the operations. This is what they're going to call everything. It's kind of universally accepted, although it's not standard. Nobody says a stack has to have a pop and a push on it. But what do we store? So let's see what the author thinks. I've already told you what I think, but let's see what they think. So what do you store in our stack collection? Could recreate our stack every time with a specific type? Very inefficient. I see what this is referring to. What data items to store? You're trying to make a stack, actually, very generic, hopefully. So it can store floats, integers, numbers, characters. Instead, create a collection once, reuse it over and over again. It can be of any data type. Must maintain type compatibility and type checking, hopefully. And let's explore some possibilities using inheritance and polymorphism, actually. So let's talk about inheritance for a second. So the object-oriented programming inheritance means to derive a class from a defined definition of another class. Hopefully we are familiar with the concept, at least. So creating a new class via inheritance is faster, easier, and cheaper, because we can take a collection and turn it into a stack. Take a collection and turn it into a queue. Inheritance is the heart of software reuse in terms of the technology. So the word class comes from the idea of classifying. Actually, from classifying as a word, groups of objects with similar characteristics. So a class is a collection. It's an unsorted, nonlinear collection, if you think about it, as a data structure. Because a class has data members, member functions in there. It's a collection of stuff in there. Class variables, instance variables, all sorts of different stuff. It is by default a collection. For example, all mammals share certain characteristics. In our example, we're going to look at the warm-blooded. They have hair. These are mammals. They bear live offspring, usually. So, in software, a mammal class would have variables and methods that describe the state and the behaviors of the mammals. And from that class, we can derive a horse class, as an example. A horse class would inherit all the variables of a mammal class, but then they would add a tail and strong legs and other characteristics. It could also define additional variables of its own that makes it unique to a horse. The original class that's used to derive a new one is called the parent class. Then we have the superclass or the base class. This one below it. A little review of object orientation for you guys. The derivation process establishes and is a relationship between the two classes. So we actually have a method that says, is this class a mammal? It's a horse, but is it also a mammal? Is it? So we can actually get at programmatically the identity of our particular objects and say, it's a horse, but is it a mammal? And treat it like a mammal or treat it like a horse. The example, a horse is a mammal in terms of the definition. So child classes are derived from parent classes that can be parent classes that can be a parent and have its own child. So every parent can have a child, every child can be a parent. So it kind of goes down linearly. Multiple child classes may also be derived from a single parent. So we have one single parent mammal, and then we have a horse, a dog, a human, all these different types of mammals that might be inherited from that. Thus, inheritance relationships often develop into class hierarchies by definition. So that's what we mean by class hierarchies. So here's another refresher for those of you taking the software engineering course. This is the UML diagram of the inheritance. So it's the UML class diagram showing a class hierarchy from animal to reptile, bird, mammal. And this is the mammal class we were talking about. Mammal came from animal. And then let's say from mammal we have a horse and bat. Down here, a bird, we got a parrot. And we see the hierarchy going. The Java collections are hierarchical as well. So we can relate this inheritance to the collection, and we can work with the collections as collections, and we can work with them as queues, we can work with them as stacks. We can go up and down the inheritance, essentially, and use different features depending upon what it's from. So it gives us higher control and reuse over the concepts. So the object. So the objects for a second. In Java, all classes are ultimately derived from the object class, as we've seen already from the Java class. So the object class provides a toString method, often overridden, to give us polymorphism, essentially to say, toString to convert objects to strings, numbers to strings, all sorts of different components. So the object class provides an equals method that tests to see if two objects are the same, or the aliases, and is it also often overridden to say that, is this class part of that class? Is this object, equal to, or is this object part of another one? And then we have the polymorphism concept, which I've mentioned already. We see a lot of polymorphic behavior with abstract data types in Java. Because if you think of the concept, are you storing a stack of numbers, a stack of strings, so we have to build polymorphic behavior into that stack abstract data type in order to, actually we don't have to build it, it's already there for us, in order to store different elements and not limit the concept to just one item. Otherwise we'd have, like what we have in C++, we have a stack that stores integers, or a stack that stores objects, or stack that stores numbers, and we have like 5 different stack structures. So instead we just have one, and it's using polymorphic behavior. So if you're not familiar with the concept, the term polymorphism can be defined as having many forms. It transforms from one form to another form, and it can be of many forms. Polymorphic reference is a reference variable that can be referred to different types of objects at different points in time. It's kind of like the C in and the C out to C++. We can see out anything. Doesn't matter what type it is. It prints something to the screen for us, and vice versa. It's polymorphic behavior. The specific method invoked by the polymorphic reference can change from one invocation to another. It doesn't always have to be the same reference. So the polymorphic results in a need for dynamic binding, which is why it's more supported in Java than it is in C++. C++ doesn't have any dynamic binding. And you're wondering, what is dynamic binding? In a programming language, that means what time in the execution or in the compilation or in the writing is the type bound with the data that's being stored with it. Some refer to it as early and late binding. Some do static and dynamic binding, described in a lot of different ways. But for the purposes of Java, know that everything is late, which means it's done at runtime. So early binding is when you make the association before the program is actually compiled, or at compile time, while the program is actually, that would be early. Late is after compilation. So Java runs in a JVM, virtual environment. All the memory, all the information is bound at runtime, which gives us the ability to have polymorphic behavior. So if it's right before execution, if it's being bound at compile time, we don't have that much flexibility. If it's a float, it's a float. We can't put a string in a float space or something, and vice versa. It's not going to work right. We have typecasting and conversion going on. So usually binding of a call to the code occurs at compile time. Dynamic binding means that the binding cannot occur until runtime. So dynamic means it's happening at runtime and not at compile time. So in Java, a reference that is declared to refer to an object of a particular class can also be used to refer to an object of any class related to it through inheritance. Which means if you create a collection and you create a stack, because we have late or dynamic binding, we can use it as a stack or we can use it as a collection. We're not stuck. We can actually go back through the inheritance of that object and use it in terms of its instantiation. So here's an example. We have mammal pet. And this is I'm going to assume that you have some programming experience, hopefully in Java. You don't have to. I think we're making a new instance of this particular object and we're calling it pet, and it is of the data type manual. Then we have horse, a secretariat, that's going to be equal to new horse, creating a horse. And the pet is going to be equal to secretariat. Well, we made a horse, but a pet and a horse and a mammal, we seem to already, through inheritance, are of the same object type. It's just one is, a mammal can be a horse. So this is going to work for us. But in this particular case, it's not going to work for us because we went from a lower level of the hierarchy to a higher level. So if we go from the higher to the lower, it actually does work. So this is polymorphic as a result of inheritance. So this actually works as a valid assignment, pet is equal to secretariat, because we're in the same line of inheritance and we're taking advantage of the polymorphic behavior. In some cases, depending upon how we are in the chain, you might be some small logical differences in terms of how it's implemented, how you're going to write it. But for the most part, if it's in the same line, it's equivalent, or it can be used in an equivalent kind of way, such as that. So using polymorphism in inheritance, reference of the type object can refer to the object of any type. So we have a generic object kind of concept. So we could use a store object reference to our stack, allowing us to store objects of any type, where we come out with that concept of the object. So that's the route that Java has taken, essentially, in terms of our stack is going to store objects. Anything that is inherited from object is an object. So anything can be stored in the queue. So we can have a queue of animals, a queue of horses, a queue of anything we want, essentially. Or a stack, I should say. So if we create something interesting, so this creates some interesting problems, and here's one here. Animal creatures equal to new mammal 10, creatures 1 is equal to new reptile. Should not work, but it does compile, because objects are all equivalent. We're not going to get a type check error. And that's one of the interesting things we get, especially when we start implementing some of these structures in Java. If everything is of the object reference type, never going to get a compile error. Never going to have a problem. But the logic, going back to what I was saying about the logical part of it, might not actually work. If you're putting a reptile in, and a reptile, if you go back to the inheritance line, reptile is part of object, but reptile is, where's reptile? Reptile's over here, mammal's over here. Not going to fit. Although they're all animals, we're going to have some slight problems in terms of the logic. Although we're never going to have a compile error to that. So one of the things you kind of have to keep in terms of concept is keeping it generic, but also making sure that your logic is correct. Because, in the old days, if something compiles, we would think, oh, it must be correct. But when working with Java in particular, a lot of things compile that aren't correct in terms of the logic. So, in terms of the generic type, one of the solutions is using an object that does not provide us with some sort of a type checking or type safe solution for our collection, which means we can easily make mistakes if we're not type checking. We don't have any type checking, essentially. So Java enables us to define a class based upon a generic type, which is the object. So this means that you can define a class so it can store, operate on, or manage objects whose type is not specified until the class is actually initiated. So when we initiate, in fact, this is kind of going back to the binding question, or the binding scenario. Everything in Java is late bound or dynamically bound, which means even the value or the instantiation of an object is bound at runtime. So until we can create an object, anything we know, mammal, space, pet, and we've created an object and it's null, it's not storing anything. But when we say pet is equal to new mammal, oh, all of a sudden we've instantiated it with a type. And the binding actually occurs at runtime right there. So until it does, pet doesn't have to be a mammal. Pet can be an animal. Pet can be something else, as long as it's compatible in terms of the object type. But when we assign it, that's when we come up with, oh, that's when it's going to end up being this type. So assume that you need to define a class named box, and that stores and manages other objects. Here's a box class, box. And it's going to be of type T. So the declaration and the code that manage the box objects of type T This is what's referred to as a dynamic assignment of the type, which is related to the concept of, this is, we're going to say this class box is of type. It's going to be compatible with the type in this particular example. So here we have a couple more examples here. So if we wanted to instantiate a box to hold objects of widgets in terms of a widget class, we would say box widget box 1 is going to be equal to box widget. So we saw this if you took the Android class. Most of you took that Android class. We saw this in the Android class. Because what we did in that class is we had, I can't remember what it was. It was like a list of something, and we had to change the object types. I think it was the Android class. I don't think I did this in the Java class. Right? It's a form of, it's not type casting. It's because casting is a C++ word. In Java, it's converting. It's taking a box and converting the type or specifying the type as a widget instead of something else, which you don't normally run into until you start looking at how are we going to create a generic type. And then if we have a generic type, how are we going to specify what type we're putting in there, make it less generic in terms of our implementation. And it's kind of a rare instance that you actually run into this situation until you start working with data structures. Something that's inherently generic that you have to add something to. And then if you start looking at the object concept and you start going, well, an object is a mammal, it's also an animal, it's also all the different pieces it could be. And in the Android class, we took an object and we converted it to different object identities, essentially, by using this type of notation. But if you didn't take it, don't worry about it. This is an example of essentially, and the book goes through a couple of other examples as well, of how you would take and hold objects of widget class as an example. And widget is nothing more than the class. It's the object type that we're saying this is going to be a box of widgets. Box 1 is equal to a new box of widgets. So if I had a box of something else, gadgets, here we go, here's some gadgets. We can also instantiate the box to hold objects of gadget class. So here box gadget is box 2. They're both boxes. They're both of the boxes, but boxes is holding gadgets and boxes is holding widgets. So we have two separate structures data structures that we're using that are both type box, but they're holding different types of objects. And this is how the Java collection works in terms of how you're going to create these items. And I'm going to go through in the next couple weeks lots of different examples of how to create these. And you'll be doing it yourself in some of the assignments that you'll be doing so. And I highly encourage you to actually use Java. It's a lot easier. You don't have to follow this. This only works in Java. You can't do this in C++. So you can't have a generic type. And this object box, which is going to be this collection that we've established, doesn't. Number one, the collections don't exist. You have to actually create the collection in C++. And number two, you can't change it. You can't have generic types like this. You can't specify the type. So the only thing you really can do is typecast. But you're taking something and turning it into something else. Here we're just treating it like something. We're taking something generic and saying, you're a widget, or you're this, you're a gadget. You're that, okay. And it just kind of polymorphs into what it needs to be. So. And don't get me wrong, C++ it supports polymorphic behavior, it just does it differently. Just implements it slightly differently. So generic types, the type is supplied at the time of the instantiation, replaces the type T with whatever is used to the declaration of the class. So whatever we're going to hold in there, generic types such as T cannot be instantiated. So we can't say widgets, gadgets, we have to actually apply it. So use generics throughout the book to develop collections of classes, essentially. So you're going to see this in most of the examples. And then we have interfaces. So Java interfaces, the programming construct of the Java called an interface. We looked at this in the Java class, actually, if we've taken it already, interface class. If not, we're going to see it coming up in the current Java class. Convenient way to define operations on a collection in terms of the concept. So we have interface classes, but we also have the concept of the interface, which gives us our public methods, gives us our ability to enqueue, dequeue, pop, and push, and all of those different functionalities that we're going to use. Java interface lists the set of abstract methods, no bodies, just the abstract methods that the class implements. kind of like the specification for the class without the implementation on the class. Provides an easy way to establish a formal declaration of the class, which will respond to particular sets of messages or method calls. So the interesting thing about Java, as a side note, is we can take a class and we can implement several interfaces. So when we implement the interfaces, then we can really create some multiple lined inheritance, essentially, where we've got multiple different types. So the stack is a collection, but it's also something else, and it's also something else. And we've implemented the interfaces to give us added functionality in terms of the interface. And the interface is nothing more than, this is the way we're going to deal with it. This is the way we're going to, these are the functions, the methods that we can run on this particular structure. So here's a stack abstract data type interface. And so it says public interface. So the word interface here, if you haven't taken the Java class yet, we're going to see it. If not, if you've taken it already, hopefully this will bring back some memories. It's not a class, it's an interface, but it looks like a class. Some people call it an interface class. Technically it's kind of wrong, it's really just an interface. You use the interface in a class when you implement it. But anyway, we have the stack abstract data type, we're going to put the type in there. And so to add an element to the top of the stack, we have push, pop, peek, we have all of the different, this is the type, public T. It's kind of, it probably should have used the word type in this lecture, maybe would have been more explicit, but don't think that this is syntax, this is the data type is the T. So what we're looking at, though, is a bunch of empty method bodies that we're using. So if you're going to create a stack, you're going to have to implement a pop, a peek, and a push. That's what this is saying. And here's a continuation. We have an isEmpty, a size, and a toString. So most of the data structures are going to have a generic toString to it. That's going to say, you know, convert this something, this object, into something I can print. Which is basically going to make it readable. So. And here's the UML description of the stack, or excuse me, of a set abstract data type interface. If you're familiar with UML notations, it looks like a class actually. A class notation with the interface, it's going to be called a stack abstract data type. Anyway, these are just, we would have data in here, but this is just the methods. The interface doesn't normally have any data. It can, but it doesn't have to. But it usually has the methods. And the methods are going to be the push, the pop, the peek. So, and you'll see that in a lot of the documentation for Java. You'll see it sort of in a UML format showing you the methods. So using the stack, stacks are particularly helpful when solving certain types of problems. Consider the undo operation of an application. So you've got, you're writing your own version of Microsoft Word. You can undo. You can undo changes. In fact, that's how the undo works. You load all that stuff on a stack, and then undo the last one, undo the last one, undo the last one. So that's a perfect example, actually, of an implementation that you wouldn't want to use a queue for. You know, I'm going to use an undo. Undo is going to use a stack. Keeps track of the most recent operations in reverse order. Postfix expressions. So let's examine a program that uses a stack, let's say, to evaluate postfix expressions. Actually, history is normally stored in a stack as well, in terms of history of commands that have been typed in, history of anything. Log files are normally stored in a stack format as well. And here's our postfix expression. The operator comes after its two operands, and this is kind of an example of why runtime environments use a stack, because we have the ability to kind of switch and understand. After we've taken in all the data, we can understand what the operation is all about, and then we can do it. So we generally use infix notation with parentheses to force precedence. So here we have 3 plus 4. Add this together, then times it by 2. Postfix notation, we would write it as 3, 4 plus 2. So, and we put the items first, and then we put the operand second. So, depending upon the order in which this is received, we can say, okay, we have items 3, 4, add them together. 2, multiply it. So if we used a stack for this, we would say, and this is very, very similar to like how programming language would be converted into machine code for stack implementation for runtime environments. We'd say 1, 2, plus. Okay, so put it on there, you go 1, 2. Take 1, 2, add them together. 3, 4, multiply them. 5, 6. And it allows for kind of an easy way of going through instruction sets. So to evaluate the postfix expression, we scan from left to right, determining the next token in the operand and the operator and operand. So if it's an operand, push it on the stack. If it's an operator, pop the stack twice to get the 2 operands. So, and then perform the operation and push the result back onto the stack. This is actually what the runtime environment is doing. It says integer I is equal to 5. When you've created those structures, I want a piece of memory. Put this at the memory. It kind of uses this sort of logic to say, okay, memory, okay, take the next 2. Okay, delete it from memory, okay, take the next 2. And it knows how many items to pull off given the instruction that was told to do. So it's just following a routine, essentially, or process. So at the end there will be 1 item on the stack, which is the value of the expression. So stack's meant, as I was basically saying before, meant to be emptied, meant to be putting things on and then taking stuff off. And here's an example here, using a stack to evaluate this postfix expression. It's 7, 4, 3, top's now 12, and we're continuing and continuing and continuing. Eventually we have 1 left. And it's a way of, think of this sort of like an algorithm, if you want to. It's a way of algorithmically going through and evaluating the expression by constantly popping off. After you've pushed everything on, constantly popping it off to get down to your last item. And then pop that off and do something with it. Use it as the final value. So going back to our postfix expression here, to simplify the example, let's assume that the operand to the expressions are integers. And our solution uses a linked stack. Linked stack. That's a new word. Through an implementation of a stack. So stack can be used. A linked stack is nothing more than a structure that's going to essentially be able to link the items together by either memory addresses or some other mechanism that might be available. So here we have, and so don't think of it sort of like a linked list, which is a little bit more complex actually in terms of the concept. So here's a demonstration of the stack to evaluate postfix expressions. And now we're getting into a class that we're going to call postfix if we're going to actually implement this. And we're going to read everything in. And here we have our expression that we're going to create, 2 expressions, and then we're going to essentially have a result for an integer that's going to be stored at the end. And it's going to go through and evaluate it. So don't worry about the code example actually. It's assuming that you already understand Java. But it's a kind of example implementation of, and you can download the slide set and kind of go through it on your own to see sort of how the source code works, but there's too much code in here. I'm going to just skip through it. And it makes a huge assumption that you actually understand the concept of programming in Java at this point. So here's a UML class diagram for the postfix expression program. This is a little bit easier to understand without all the implementation details. So we have the array stack used for the implementation. There's our stack abstract data type. And then we have our postfix evaluation. We have our postfix number that we're going to end up with. So our main program that works with an evaluator to read the items in, to build the structure, populate the items into the structure, essentially, and then perform the operations on the structure in terms of its development. So do you have to create something that's complicated for your particular assignments? No. Everything will be a little bit less complicated in terms of the implementation. So, because usually at this point students start freaking out. They're going, wait a minute, we have to write all that stuff when we implement the collection? And so the good thing is actually the book gives you, which is why I highly recommend getting the book, gives you the source code examples. Every one of them is in the book. So that code just came from the book. So there's a collection. I'll leave it to you and some of the assignments to actually implement some of that stuff. And you may use anything you find in the book. It's free game. So, exceptions. So collections must always manage problems, situations. So this is why we have the is empty. Why do we want to pull something from the stack if it's empty? These are done. So example, attempting to remove an item from an empty stack. Designer of the collection determines how it might actually be handled. And in our particular implementation, it provides an isEmpty method, which we have. So the user can check beforehand and say, is it empty? No. Okay, pull an item off. Is it empty? Yes. Okay, we're done. So it's kind of like the null, or the null character at the end of a string. And it throws an exception, and in a situation that arises, so we can catch the exception. So we can use a throws on our class and use the built-in Java exception handling. The collection class actually has its own exception handling, which is great as well, because you can pick up different, the structure's empty, or the structure's too full, or there's past, some problem happened, something erred. So stack can be empty. What if can it ever be full? Depends on how you define the structure. Intuitively, the underlying data structure, the array link structure, etc., could run out of memory. There's actually cases in which the runtime environment runs out of memory. It's dynamic, but it's not without resources. The computer might actually run out of, the environment might actually become full. Conceptual stack collection cannot be full, usually, by concept. Thus meaning the capacity is an issue with stack implementation, which means, as I mentioned before, you set the capacity. So I only want to run 20 instructions at a time, or 30 instructions at a time, and then it does it in batches. Fills up the stack, runs it off, fills up the stack, and it knows when to stop filling it up. So in terms of managing the capacity, a couple of notes on that. Obviously, an array is going to be fixed. So an array has a particular number of cells when it is created. It organizes by a structure at its own capacity. So if we were going to use a stack, you probably could use an array if you know you're going to have 20 elements, 15 elements. So the array's capacity is also stack's capacity. So a lot of stacks, believe it or not, in non-Java languages are implemented in the form of arrays. So it's kind of easy that way. You just pull it off in the reverse order and put it on. So you can take an array structure and implement a stack abstract data type from that. And the underlying structure that you're using is an array. Most people would take the next step and go, well, if it's a queue, probably going to use a linked list. That's what you're going to do. Instead of an array, maybe not. Maybe you can use an array for that. There's no law that says you can't use an array for it. What do you do when the stack is full and the new element is added? You can throw an exception. So Java actually has its own exception handling, as I mentioned before. It can be thrown to say, hey, your stack is full. You can return some kind of status indicator to the user. You can automatically expand the capacity, add another array. Here's another stack. Here's another stack. First two options require the user of the collection to be a guard and deal with the situation as needed. The user's not going to sit around and go, okay, make it bigger. Okay, add another one. Not going to work. Third option is best, specifically in light at our desire to separate the implementation from the interface, make it grow dynamically, or cut it. So the capacity of the implementation problem that shouldn't be passed along to the user unless there's a good reason to do so. And that's just a software engineering kind of an approach to it. Don't make the user make the structure bigger. If you think about it, though, isn't that what most databases do? You run out of table space, and so the user makes the table space bigger, adds more data to it. So basically, it's saying that that's wrong. You should have the structure dynamically get bigger if it needs to. In terms of exceptions, the problems that arise with Java programs may generate errors, exceptions or errors, and the exception is an object that defines an unusual or erroneous type of situation by definition. An error is similar to an exception, except that the error generally represents an unrecoverable situation. So an exception, an error, if you throw in an exception handling, you can put in a handler to deal with it. So programs can be designed to process the exception. One of 3 different ways. This is kind of some generic programming methodologies for you. Not handle the exception at all. Don't even catch it. Don't even worry about it. Just let it go, which is not safe for the program, essentially. Handle it when it occurs. Handle it at another point in the program. So if the exception is not handled at all by the program will produce an exception message and then terminate. As an example, here's one here. Arithmetic expression divide by 0. That happens all the time, actually. Who's going to catch that one? Especially if that only happens once or twice. A blue moon and stack filled up or something. The message provides the name of the exception, description of the exception, and the class and the method that the exception occurred in, as well as the file name and the number where the exception actually occurred, which makes it handy. So, to handle an exception when it's thrown, you're going to use a try statement. So this is the method here to try, which consists of a try block followed by one or more catch clauses. This is very similar actually to C++. So if you're not familiar with the exception handling, this isn't your how-to. This is just an example of how you might want to implement it in terms of the Java implementation. And say try, put all your code right here. Catch this IO exception. It might be stack's full. Handle the IO exception problem somehow. Eliminate, create a new stack or something. When the try statement is executed, the statements in the try block are run, so everything is executed. No exception is thrown, the code never makes it. It continues to the next statement after that. If an exception is thrown, then the control is immediately transferred over to the catch. It catches it, deals with it, and then continues on if it can. So in the catch, you can put those exits. And you can put that terminate the program kind of statement if the exception is significant enough. So, if an exception is not caught and handled where it occurs, control is immediately returned to the method and then invoked by a method that produced the exception. So it goes backwards. If the method does not handle the exception via a try statement, then the control returns to the method that called it. So control automatically just goes back to the calling method. So how you deal with exception is really up to the programmer in terms of the design. So, and exceptions occur a lot with data structures because you build the perfect world and then someone comes in and it messes it up. So either the file didn't open, it's storing the data, the database didn't open, connect properly, something happened, and it seems to happen a lot with data structures. It's because of the nature of the job. You're manipulating data, storing data, searching through data, something's bound to happen. So the process is called a propagating the exception. Some more terminology for you. Exception propagation continues until the exception is caught and handled or until it's run out. It's finally gone back to main and the program actually terminates. So I am actually going to stop at this point. We're not going to go through the whole lecture today. What I want to do is talk about array implementations next week in terms of the array stack class. And what I'm going to try to do is bring in some examples of some Java stuff to show you the exception handling, to show you how to actually create instances of collections. So somebody remember I stopped at 1-58. I believe this slide set only has 68 slides, so it's about 10 slides short, so I'll probably figure that out. But, so next time we'll hit arrays, stacks, array stack implementations, because what's going to end up now is we're going to start implementing stacks, structures, so we can kind of see the data structure come to life. So, and I will also try to remember to go over your first assignment next week as well, because usually it's time to start thinking about, as soon as we go over a structure, to start thinking about implementing it. It gives you some time ahead. So, questions, comments, or concerns? Nope. Then we're done for today.